So all this esoteric stuff, and the next question is, let's just go back to something we really know and see whether we really know it or not. Okay? And hopefully the answer will be yes. And you guys are getting a little anxious. But I do have 2 minutes, and I really am short of time. So I'm going to use these 2 minutes. Okay? So I can do, I wrote the Java program first. I don't know whether I wrote the C program first, but I did a very mechanical translation from one to the other. And it was so mechanical that I'm sure I can write a program to do so. And if I can write a program to do so, then I'm surely not using the full power of Java. So, but I can do what I did in C, and there's not much difference. Okay. So I have the IO and main. Okay, and I'm just inputting a little differently. I'm outputting a little differently, but otherwise things are same. Okay, and here's my logic. Okay, and the question is, let me leave you that with that question. Given this problem, how could I make better use of Java? Okay, then do what I just did here, which is take my C program, translate that into Java. My modular C program, I didn't take my monolithic main. I converted that into different functions. I removed all duplication, but I'm just converting my C file to a class file. Okay, that's what I'm doing. And if that was sufficient, then we don't need all the extra stuff that Java gives us. So I want to motivate here the reason why Java has more than C. Okay, and let's try to motivate that using this example by saying, hey, this was not quite done right in the C solution. Even though it was more right than the monolithic main, it's not right enough, even in this example. Okay, so think about that, and hopefully we'll finish. I know we'll finish the overview by the end of next week. It may not be by Tuesday. And in the meantime, we'll try to keep you busy with some assignment features. So the big thing last time was declarative versus non-declarative. And I asked you guys at the start, what is the opposite of declarative, and give me an example. And I got an answer that I somehow fit with what I was expecting, but I later realized right after class that the intent was something else. So Nick was the one who gave that answer, and he said, look, use of magic numbers is declarative, and not using it is non-declarative. And I assume what you were meaning was that there is inferred and declarative. That the first piece of code here says a regular pass is true if a total is greater than or equal to 60. I don't go and say anything about what 60 is. It's a magic number. In the next piece of code, which is also ML code, I have declared a magic number that I might not have declared otherwise. Okay, and so that's declared. But I didn't declare any types. I didn't mention any types. And the third example is from C, where I actually say the total score is double and the return value of regular pass is Boolean. Okay, so that was not quite what I meant, but that's a very good interpretation of what I was asking, because I said, what's the opposite of declarative? And there can be multiple definitions, multiple interpretations there. So that's very declared versus inferred. Okay, and that's making it easier for the programmer to understand things. They don't have to write the inference algorithm themselves. Okay, what we're really talking about was declarative versus procedural, where in one case you explain what you want, and in the other case you say how you want it. Okay, and how you want it can be specified at multiple levels of detail. Ultimately, you can go down to sort of the machine level or even lower microprogram level and have full control. But procedural means you have some control, whereas declarative means that you have essentially no control in pure declarative. Okay, and so we saw that when we declare something as an array of floats, we really have no control over how the floats are laid out. Okay, we've just said that we want an array of floats. They could be laid out as the compiler wants them to be laid out. Okay. Whereas when we wrote a sum function, we decided it was not going to be a recursive function. It was going to be an iterative function, which was going to use a loop. So we made some choices, and so that's procedure. Okay? So in a single language, some things could be declarative, and some could be procedure. So we then said, so that's complementing. And can we have something competing? That in one mechanism, we have pure procedural, and one you have pure declarative. And in your 455 course on automata theory, I assume you learned all of these things to some degree. The linear bounded automata is something that's never covered in great depth in automata theory courses, so I'm not surprised you guys just heard of it. But the other three machines, I assume you learned. And we saw that, there's the automata, and then there's the language, expressions and grammars that are the declarative equivalent. Okay? So one gap that you guys didn't cover in your course was that what's a declarative equivalent of a Turing machine? Okay? And that is the gap that we're covering here, which is logic programming. So logic programming, again, this is a tour. We are not looking at things in depth, real depth. When we look at things in real depth, we look at the actual implementation of these concepts. Okay? So we'll actually look at the implementation of Prolog when we look at it in real depth. Right now, we are looking at it sort of by example, as you might learn things by looking at Stack Overflow examples and seeing how you can generalize those examples to your code. Okay? So we saw some code. Okay? I asked you guys to interpret it, and you were kind of lost first. And then Nathan interpreted it using what he knew from procedural languages. Sorry, you were the one who interpreted it, right? And I'm trying to remember the names. It's been 3 days or 5 days. It says, well, the first line says assign to pass cutoff 60. Okay, that's what it means in other languages. That's what it must mean here too. And the other lines, like regular pass is a function that takes as an argument total, and its evaluation is an OR of the expressions on the right. Okay, so that's pretty much looking at it in a very functional way. What's different here is that something can be assigned a value multiple values that are all existing at the same time. Okay, we don't see that in the example of pass cutoff, but I could have said is a Grand Slam winner. I took a tennis example last time, and I could have Cilic there and Nadal there both. And then I could have some rule that says, are you a good player? And you're a good player if you've beaten a Grand Slam. Are you a really good player? And you can say you're a really good player if you've beaten a Grand Slam winner. And there's more than one Grand Slam winner. Okay? So I could have had a Grand Slam winner as the keyword, as the name of the fact, and a string as an argument. Okay? And you see that multiple definitions in the highlighted text. Okay, so in normal programming languages, given a signature of a method, okay, in Java-like languages, given the name of a method, you can have multiple signatures with the same name. That's called overloading. Okay, here you can have multiple. If you think of this being method definition, the rule being a method definition, you can have multiple bodies for a method. Okay, so you have two definitions of pass, which both take the same arguments. Okay, and the whole idea is that you're trying to prove something, and you try to prove, and you take a path, you take one of the definitions, see whether you can prove something that you want to prove, and if you can't prove, you backtrack and try something else. Okay, so this whole notion of backtracking is extremely important, and in the process of proving a rule, you might go and assign values to variables, which you undo when you backtrack. Okay, so I gave you the sort of real-world example of, hey, you've taken this course to try to graduate, things don't work out, you try to take another course, and then come up with another plan to graduate. Okay, so that might be a more realistic example. But here I have got two definitions of pass. I'll try one. Who knows which one I will try first? And if that doesn't work out, I might try the other one. you come up with a whole tree of branches. Okay, and whereas in a regular language you will take one path through the tree and be efficient, here you might end up taking a lot of paths, and it might be exponential, but that's what you get for not doing the how. Yeah.
How does it know which one is correct? Like, let's say it's like an int return. How does it know which one's right?
It doesn't. It doesn't know which path is correct. Any path that leads to success is success. Okay, so I might have one path that leads to the fact that, so somebody might not have beaten Nadal, so we won't say they're not a very good player. We'll try Cilic next. Okay, so it doesn't know. That's the whole point. So it's going to try everything. It's brute force. But there are ways in which you can guide it, just to make it practical. But that gets to be beyond, that's cheating. So there's a lot of cheating that goes on when we try to come up with these pure things. We ultimately end up going to some procedural language idea. Okay, but it doesn't know. It knows something is correct if there's a fact to which it can derive. So if proving that somebody has passed, with a total and final, as long as they can take a path that says yes, the expression is true here, then it will say it's true. And if it can't find a derivation, it'll say, to the best of my knowledge, it's not true. It never goes and says this is false. If it gives the answer false, it's saying to the best of my knowledge, based on the facts you've given me, I can't prove this. Okay? There was another question?
That was what you said afterwards.
Yeah. Okay? Okay, so that's where we ended. And then I said, should we even bother with Java? Okay? That's something you've done in Foundations of Programming class, Data Structure class. If you've taken compilers, probably in the compiler class also. So, do we really revisit it here? Okay? And I assume you guys know the Java constructs pretty well right now. I mean, the popular ones. I don't know Java. I think there's too much of Java. But the popular ones, I think I know. Okay? And the question really is not so much do you know or do you know as to do you know how to use what you have. Okay? So on the surface, even if you didn't study Java, even if the TA never studied Java, he basically told me, look, I know other object-oriented languages, I know other languages, not a big deal. Absolutely, he's right. Okay? And here, I took the C code, I literally, as I mentioned last time, did a one-to-one copy and I got a Java program. Okay? And here's sort of the part that does the main and the input and output. Okay? And here's the part that does the logic. Okay? So I transformed a C program into a Java program. And now let me ask the question that I posed at the end of the last class. So is this, for this example, was this a good use of Java? And we really have to put our pure hats on. I mean, does Java look good with this example? Does Java look good comparison to C? What's bad about it? Mark? Sorry, yeah.
I mean, all the methods are static. First thing I saw, you're not really using the fact that it's not recorded.
Okay, so right now Java looks pretty bad because I had to go and put the static keyword here. So when Java first came in, people said, oh, look at the hello world program, public static, which you don't have to do in C. So static is sort of the next level. What about public? Why did I have to put the public keyword here? I didn't have to do that in C. So what do I get? So we get something by not having it static, right? What do we get by having the choice? So it's good to have the choice of saying static or non-static because we have two choices. Okay, more choices maybe makes the program more interesting or better. And we'll get to that part the next. Let me first ask you, what about public? Why do we have to put the word public? Yeah. So you have control over access qualifiers. When you say access, you're saying there's us and there's them. So what is the us and where's the them? Who's the them? So in C, the way I presented C at least, everything was one big file, right? There was no them. It was like an open community. And when you talk of classes now, you're saying classes defines some access scopes, okay, some walls. It's like saying our community will not be two gated communities, and we'll be very careful about who goes from where, okay? And when I teach 401, I always tell them that classes have two roles, okay? So what is public for? Public basically says that we have divided our program not into one monolithic sequence of procedures and declarations. Okay, we started off by making a program one monolithic procedure. Okay, and Chris said, so what's wrong with that, right? And we said, well, there's this whole reuse issue. Okay, and if you did like my procedures, modularity, now I'm saying you won't like this, which is that we become even more modular, and we say this part and this part are somewhat independent of each other. So they are modules. We still have everything static. Okay, this is how historically it happened. Things were all static at one time, and then people said, let's have modules. Okay, and modules are walls around methods and global variables. We say these variables go with these procedures, and these variables go with these procedures. They can all be static, but we'll put walls around them. And if we really need any interaction, we'll be very careful, and we'll say, okay, I export this, I import this, and can I export it? Well, so that's where the public keyword comes in. Okay, so it's an access issue. And programming languages with modules are called modular. And the first language with which I'm aware was a language called Modular. And then there was a successor of it called Modular 2. And Mesa was yet another successor of it. Okay? So we can now go and how to decompose a program into modules. That's always, you can say it's an art, it's a science. We'll talk about the decomposition soon. But here's my original program broken up into two subparts, into two classes, still static, everything is static, okay? And what I've done is I've put the main method in a main class, okay? And I put the rest of the code in a util class, okay? And now conceivably I can have multiple main classes that deal with the util class, okay? And we now have multiple scopes, so there can be ambiguity. So even though they're both in the same package, so they can access each other's methods. If they were not in the same package, we'd have to import, okay? But I still have to, now I can't just say input double, I have to say pass util.input double. So I'm getting more verbose, okay? But with the benefit of having these walls. And the idea is that you can have one set of programmers work with one module, another set of programmers work with another module. We have divided the program into multiple units, so it's easier to understand. So we get these benefits. Okay. So even if you never instantiate an object, you're getting something from Java compared to C. In C, you can have multiple files, which is kind of the same thing, but with less checking. But here, the concept is more explicit. Okay, questions so far? Okay, now we get to the harder. So now let's go to static. Okay, so we specified. So what's the difference between static and non-static? Yeah. Okay, very good. So static is something that you can call on any class, okay? Whereas a non-static method is what you call on an object, which is we know what a class is. It's a collection of procedures and methods. An object would be what? An instance of a class, okay? And why do we use the word static for, why, so, in small talk, they talked about class variables and instance variables. In C and in C++ and Java, they call it static versus non-static. So why is a class variable static and why is an instance variable non-static? You know the class at compile time, yeah?
Static can only have one instance of that object.
It's only one, static has only one instance of the object of the class, and it is loaded at what time? When does it occupy memory? At runtime when the class is loaded. And an object, you can have multiple instances, so that space for it is allocated when? So an object is an instance of some class. Yeah. When the object is created, which means when the class is instantiated. Okay. So for those of you who know something about memory management, I guess you learned this in 411. There's the heap. Did you guys study the heap? And somewhere you must have seen the heap, right? So heap is the area of memory that stores dynamically created objects. Okay? Stack is also dynamic, but stack is something that is used for procedure calls. Whereas, and so any data structure allocated in a stack goes away when the procedure goes away. Whereas heap is something that is also global, but allocated dynamically. Okay. So I think I have some text here. Static variables allocated memory once when containing class loaded and occupy space until end of process. And instance variables allocated each time class is instantiated. When does that space go away? That depends on the language. In C++, when does the space go away? Anybody know? See, that's the whole thing with heap. Heap is not tied to a scope. Heap contains global data structures. So that's the stack variables that go away. Okay? In C++, yeah.
It's either never or whenever you run free.
Whenever you?
When you run like free or delete.
Yeah, when you do when you explicitly go and say go away, space should go away. Okay? Whereas in Java, you don't have to worry about it because it's taught what? Yeah, who wants to answer? Mac is hesitating because he's answered a lot of questions. Somebody else want to answer? Oh, yeah. Garbage collection. Okay. So, now the hard question. For this problem that we've beaten to death in multiple languages, how should I break up this into instantiatable classes? Or should I? Is this just fine? How hard is it, from your experience, to figure out how to break up a program into multiple instantiatable classes? How many of you think it's really hard? One person admits it. He's the one I would hire. I wouldn't hire any of you guys. It's extremely hard. I don't care how many years you've been programming, I have never seen a good decomposition, more or less. And I use a lot of open source code. Okay? And it is so hard that, but you guys studied 401. And some of you took 401 with me, some of you took it with KMP, but we both cover something in that course that helps you decompose a program. Was there something in 401 that provided you with guidance on how to decompose? Yeah. Infrastructure, there are a lot of terms you can use for it. Infrastructure in general means something that's provided for you, to you.
It's like you just name the stuff, but you don't actually implement it yet. It's like the things you have to implement.
Interface.
Interface, that's not it, yeah.
Interface are a means. Okay. Something else?
The design patterns.
Design pattern. What's your name, by the way? Ben? Okay. Design patterns. Okay. So let me tell you the history here too. So there was a guy called Ralph Johnson who graduated from Cornell, and he looked at Smalltalk code to understand how it was written. Because object-oriented programming was new, and Smalltalk people were the ones who sort of knew what it meant. And he became a professor in Illinois. And he went and said, wow, you know, there are all these, there's some principles here. And he looked at the code, and then he came up with the term design pattern, which was, and he said, look, let me just sort of document, and this is really bottom up, he did that. And he's the one of the 4 authors of the Bible of that design pattern, which is the book, which is the design pattern book. So that's the term design pattern, okay? And have you guys studied a design pattern? And the answer is yes. So, which will help us decompose this program. And the hint, this is an interactive program. It has a So let me just ask you, did you guys study in your 401 or my 401 a design pattern for interactive programs, Robert?
Model view controller.
Model view controller. So Robert did my distributed systems class too. And so model view controller. Have you guys all heard of it? Okay. So there are 2 definitions of model view controller. Okay. The one I'm going to give you, which is the correct one, because it comes from Smalltalk. And the one that KMP might be using, because he comes from the web world. Okay. And we'll go and see whether he covered. When I cover both. So before I go there, the whole idea there here now is that when we talk of dynamic or non-static, we're talking of class being a type now. Class is no longer just a module, it's a type. You can instantiate it, and those instances are classified or typed by the class name. Okay? Ideally by interfaces, but you can type via classes also. Okay? And values of these types are created by instantiating the classes and share the behavior of the type. Defined by type. So in every language, there's a way to create programmer-defined types. Okay? In C, you will use struct. But these are all non-abstract data types, whereas in Java and C++ and Smalltalk, you can create these object types. Okay. So by this definition, a class is a template or blueprint for generating instances. And programming languages with instantiable classes are called object-based, and I mentioned Smalltalk. Smalltalk 80 was the standard Smalltalk language, so you would imagine that object-oriented programming came in the 80s. Indeed, it got popularized in the 80s, but it was invented, like all good things were, that we're talking about in this course, in 60s and 70s. So it was 67, it was similar 67, which came from Bell Labs. Okay? Smalltalk 80 came from Xerox. So double role of classes. Classes are modules that put walls, and classes are ways for programmers to define their own types. Okay? Okay, actually, I asked a question about this particular example a little too early. So before we go to that, let me just try to unite these 2 definitions. So can classes both be, I said they are double roles. Can we have some, is there some unifying abstraction that combines these roles? Okay? And to do that, I'm going to do an analogy with physical objects. So that's, when you study object-oriented programming, most people go and say, computer objects are like physical objects, let's use the analogy. And that seems to work a lot. And actually, the object-oriented programming gets more difficult when the objects you want to create don't have physical analog. Okay? So if I say, model a car, model something that you know about, you will have a car object. You know that physical object should correspond to a virtual object. But it gets harder as an example when there's no physical object. But anyway, let's go from physical objects. So if I was to ask you, are the objects in Java or C Sharp or whatever object-oriented language you've seen before, more similar to natural objects or manufactured objects, which would you say?
Depends if you're reading or writing the code.
Depends on whether you're reading or writing the code. I'm writing the code. And they're manufactured because they're more similar to manufactured objects because.
Defining how it works.
So you're also manufacturing them.
Yeah.
You're the creator. We know manufactured objects have creators. There's no dispute there, right? So that's why they're more. Okay, so you can imagine there being a factory or creation of. Let's assume that objects are created in a factory. Okay, some of them may not be. And then you have things that the factory manufactures. Okay, so if a factory, and then there are multiple things that the factory can manufacture. Okay, they all have something in common, and you can perform operations on those things that are manufactured, like accelerate. Okay, and you can also perform operations on factories and say, hey, how many cars did you produce? And do you see an analogy here with the object-oriented world? A factory would correspond to a so a factory would correspond to a static method, or a static method is related to a factory. So the num cars operation corresponds to a method in a class, which would be a static method. So the factory must correspond to a class. Okay, and the things manufactured by a factory would correspond to object. Okay, they all have the same behavior, right? The same operations. The difference is that one car might have more mileage than another car. So their instance variables may change. Okay, but the set of operations they have are the same. Their behavior is defined by the class. So a class has instances on which you can invoke operations. And static methods are just methods you invoke on the class object. Okay? So in fact, there is something that unites them. And in Smalltalk, even a class had a class. Okay, even in Java, you have the class of a class is the class. But in Smalltalk, we went even further. There were things called meta classes. So, so by this definition, so basically, it's not as if they are two different roles completely. That's why Smalltalk called the static methods are class methods, and instance methods are object methods, and they're united by this analogy. Okay. So class instance method is method invoked on class or class instance. So by this definition, I never like the analogy of class being a blueprint. I mean, it's good, intuitive analogy on the first cut, but it's more like a factory than a blueprint. A blueprint is passive. You don't perform operations on it. Whereas in a factory, you have dynamic state. It's got its own state too. In those static variables, you can hold values that change dynamically. So in that sense, a static variable is dynamic. I mean, it's allocated statically, but it has dynamic values. Okay, so it's an active thing. But this factory analogy is different from the factory design pattern, which we'll also talk about in today's class. So I want you guys to distinguish between those two things. A factory design pattern is a separate concept from the factory analogy. Okay, so factory metaphor is not equal to the factory pattern. Okay, so now I ask you the question, modular to object based, and the answer was MVC. Okay, and those of you who took KMP's class, somebody want to define what model view controller is? A design pattern describes the behavior among a set of related classes. Okay, it describes the behavior in some abstract way. So the model view controller design pattern seems to indicate there's a class that defines a model, one or more classes. There are one or more classes that define views, and there are one or more classes that define controllers. So the design pattern should go and describe the relationship among these classes in some abstract way that is formal enough that you can tell, or maybe not automatically, but at least a human being can tell whether the design pattern has been followed or not. So what's your name?
Hutch.
Hutch. Okay, Hutch, you were going to offer a definition?
is like the database and where the things are actually, the objects are actually stored. The view is like the GUI or like what's seen, and the controller is how the GUI interacts with it, updates the kind of the database or like the actual data underneath.
Okay, so that's pretty good. The model is the semantics. Okay, database makes sense when you're storing things in persistent memory and you have some properties. So it's like the semantics, the logic. Okay, the view is the UI, and the controller is the one that connects the view to the model. Okay, everybody agree? Everybody who's taken KMP's class agree with Hutch, right? Anybody who's taken my class want to give a different definition? I know there's not many of you here. That's a Smalltalk definition. That's what you will see in your Apples and Androids. At least in Apple, that's the definition that's used. Robert? See, KMP was much more effective. So view does both input and output, right? It's a UI. And in the Smalltalk design pattern, so logic is going to be like the IO and main is sort of like the view and control together. So the model is the semantics in the real MVC, which is the Smalltalk MVC, which is the first design pattern that Ralph Johnson actually found. Okay, in Smalltalk. And the controller handles input, the view handles output. Okay, and that I can actually derive this model from first principles. Okay, you want separation of input and output. There's no reason why the output and input should be combined. The input can decide whether something is provided as a keystroke or a menu or by a text box or through the command line, and the view can decide whether it's displayed as text boxes in the console or as the graphics. So the controllers, and there can be more than one controller, controllers go and invoke methods of the model, okay, whenever some new input is processed. And what does the model do now when something happens in the KMPs or the web? That's called the web MVC. In web MVC, what happens when you go and change the database? What does it do?
It might have to update the view.
So it might have to update the view, right? So in fact, that's what happens in Smalltalk MVC. So change model notifies views. So the model is an observable, and the views are observers. Okay, all this is important not only to understand why Java, how to use Java in this example, but also for your project that you're doing. The project is implemented using model view controller, and you need to know this architecture to some degree, very small degree, but you do need to know. Okay, so the model needs to update the view, so it goes and notifies the views in Smalltalk MVC. Okay. And the views can call methods in the model to get more data that was not passed to it in the notification. Okay, this is not the web MVC. Okay, and the whole idea here is that the controllers and the views are independent of each other. You can have a shortcut or a menu, and that is independent of whether something is displayed using graphics or using text. Okay, that just makes complete sense from a software engineering point of view. And observers and views can have different implementations not known to the observable models. So like I said, the fact that one view displays something graphically and something displays textually, the example Smalltalk guys used was bar chart and pie chart. Okay? And it's just oblivious to how it's being displayed. It just says there is some view, some set of views, I'll just go and notify all of them, and I don't really care how they're implemented. Okay? The web MVC, on the other hand, controller invokes a method in the model. Typically, the model is in a web server. Web server cannot initiate calls on web clients, and the UI is in the web clients. Just because how web is designed, web was not designed to do the kind of things that web is being used for right now. Okay, and it was not designed to be have data written into it by the users. So the controllers invoke methods in the model, And then the model does not invoke method in the view. The controller invokes methods in the view. Okay? So the controller is the glue between the model and the UI this way. And the whole idea there is that, well, we can't update remote views, but there may be multiple views within the same web client. So the idea is that, look, the controller is within the web client, the views there's a bunch of views in the web client itself. So the controller will go and invoke a remote method in the model, and then ask the views to go and pull the data from the model. Okay? So you can justify it only based on the fact that there is no way for the server to invoke methods in the client. Clients can invoke methods in the server. This is a whole stateless thing in the web, but not vice versa. So we go around that by having this architecture. Okay? I have tried to keep as far from the web as possible, so I may be wrong here. But for those of you who've taken KMPs, many classes, is this consistent with what you've learned? You're not sure? I've looked it up, okay? So it is consistent. Okay? So, okay, views can then invoke methods in the model. Okay? So this is not the model view controller we will use. Like I said, this we can't explain from first principles, only because of certain limitations. And, okay, here's some text that explains what I said. So, so if you want to do MVC, let me introduce sort of another issue that arises in programming language design. I said that a model or an observer is oblivious to how the views are implemented. Right? We agree on that. One can be implementing a pie chart, a bar chart, and so forth. But the model has to invoke a method in these guys. Okay? To invoke a method, I need an instance. To type the instance, based on what I've said so far, I need a class. So how can I invoke method in classes about which I don't know? It seems that I need to know the class to invoke a method. And yet I'm saying, no, it doesn't, and classes are what provide implementations. They are the factories. So how can I be oblivious to the factory if I need to type the object of the factory?
You have like a listener?
Sorry, you have a listener, but that listener is, what is the type of the listener? That's exactly, you have a listener. But how do you type the listener? So I want to invoke a method in the bar chart class and a pie chart class. So my listener is of type bar chart or pie chart or something else? Yes.
You need to have like a superclass that they would inherit from.
Okay. So there are many answers to this question. Okay. So how to make sure method calls are bound to different implementations dynamically at one time? Okay. That must mean that I invoke a method in the superclass, but that is the superclass I use to type it. But it's actually invoked in different subclasses. So when I go and make a method call, I do not quite know the address of the method that is being called. It gets bound dynamically. Okay? And so that's called dynamic dispatch. So somebody somewhere I saw, someone said that, look, C# has the keyword dynamic. And I actually programmed a little bit in C# when I was at Microsoft, just to see how it looks like, but I'm not quite sure what it means, but it might mean what I mean here. I didn't have a chance. So concrete superclass, so you're Jacob, right? Yeah. So Jacob mentioned that, look, concrete superclass defines these methods. Classes override them. And the model just invokes a method in the superclass. It names that method. And at runtime, depending on what the actual listener is, what the observer is, the method gets chosen. Okay, and that's how Smalltalk did it. C++ created the notion of defined the notion of a virtual method, which may be what the C# dynamic method is, which are methods that are bound dynamically, and they also had non-virtual methods which are not bound dynamically. In Java, is there another mechanism to do this? Or even in C#, there's concrete superclass, and what's the opposite of concrete superclass? Abstract classes. Okay? C++ also supported abstract classes. And what's something in Java that is somewhat similar to abstract classes? Interfaces. Okay? So additional concepts seen in Java, interfaces. Okay? And interfaces came, to the best of my knowledge, first in Mesa. Okay? So the interface idea and the type idea are totally independent. When we were defining modules and saying that the programs can be broken up into modules, we could define the interface of the module, which is a set of headers of the methods in the module, and then the implementation of the module. So Mesa was not object-oriented, but it had modules plus interfaces. Okay? And Java decided that static methods cannot be in interfaces. There's probably something, some implementation reason, maybe some conceptual reason also for that. But I personally would have preferred if static methods could also be in interfaces, declarations. Okay? So, so far we've seen inventions that all have to do with not niceties of software engineering niceties, but how to implement niceties. And so this is a concept that came very late, relatively. It was like, I think, late 70s or maybe even early 80s that Mesa came around. So this is actually one of the later concepts in what we're discussing. Okay? And the real world analogy for interfaces is that you have factories, and you might want to have a specification of the factory. So you want to duplicate the factories. You want to have more than one factory, and so you want to have the specification of the cars implemented by the factories, and so that specification can be independent of the factory, so you can have multiple factories. Okay. So interfaces are good for dynamic dispatch, okay, because you can just define the method headers. You don't even have to describe any method bodies here. Any other uses of interfaces? Give an outline, okay. Specification, that's the analogy, okay. And also replacement. You might not only want to have multiple implementations of the same object, like in model view, but you might have a view that's dependent only on, let's say a view can display only one kind of model. That kind of model is specified by the interface of the model. The actual model doesn't matter to the view. Okay? So the view so it can be replacement, and the most important, it's a specification of documentation. Okay, so again, I'm going to say one of the goals of programming languages is to reduce the amount of comments you write, the number of comments you write. And by having an interface, you just give the outline, and it's understood by the programming language. You can check the outline and the implementation to see whether they're consistent with each other. So, and if you program in C, what corresponds in C to an interface? Header files, exactly. No, they're exactly that. Okay. And so the .h files are the ones that correspond to interfaces. Okay. So when I teach 401, I require every class to have an interface. Okay, and I actually have code that checks that. And I'm sure no other instructor ever required you to do that. And I think concepts should be reinforced. So in the code you implement, and you're not going to be implementing many new kinds of classes, so this is not going to be a real issue. But I do want you guys to follow this rule, and that will replace comments, some comments. Okay, so every class should have an interface, which is like an outline, so that we can look at the outline without looking at your class. Okay, and we may or may not grade you on that, but be ready to be graded on that. Okay. And each object variable should be typed by an interface, never by a class. to give us that flexibility.
Are we not allowed to put comments in the interface to explain what it
You know,
is, or do you only want it there, not code?
you can have comments everywhere else too. I'm just saying to reduce the need for comments, have interfaces. Okay, and to increase the chance of reusability, type variables as interfaces rather than as classes. Okay, just never type a variable as a class. Yeah.
Interfaces do not implement methods, correct?
Interfaces traditionally do not implement instance methods. They can in new Java implement static methods.
So with that, I don't understand the comparison to like a header file in C, because you can have like full implementations of things in header files.
Yeah, so it's, that's why it's approximatory. C has only static methods. In Java, you can have static methods and interfaces. So the comparison is actually valid. But we're not going to, so ideally, you should have static method headers also. That is what Mesa had. Okay? So it can be done, and it has been justified. Okay, so I can declare constants in interfaces. So here I've got a model that describes the interface for my for the object that will go and have the logic for grading for passing. Okay, so you can go and get total score, set total score, set. I don't have a separate method for setting total score and final score because I assume they go in pairs. Okay, so I have a set scores method that goes and gives you the total score and final score, and then I have an isPass method that you can call to figure out whether that the last set corresponded to a pass or not. And then I have also a getter method in case you need it. Okay, in case the view needs it to display it. Okay, so small piece of code. Any questions? Okay. So add property change listener. Okay, so what might be confusing you guys is this type, property change listener. That's just a predefined Java type, and that's a type that defining a standard observer. Okay, so it's got you guys can just look it up for details, but it is a Java observer interface. So because this is a model, it has not only got the set scores and getter methods and isPass method, but it's also got a method to register a listener. It's a model, it's an observer. So somehow you have to go in a view or, observable. And an observer or view must register itself with the model. So it's got this add property change listener. Okay. Nathan, you're looking at it in a puzzled way. Any questions? So what would the view of this model be listening for? Mac? The view is listening. The view is the output. So the interaction is that the user goes and inputs final score. The user inputs total score. The model computes whether it's pass or not pass. And the view will do what? Display the result. It's listening for the new pass value. Okay? Which will happen to be a property that changed. Okay? So ideally, the interface should make sense without the implementation, right? If it's well documented and well commented, which is the argument you were making earlier. So add property change listener is a method that the view calls on the model to register itself. Okay? And we will have an abstract model class, and we won't actually keep the list of observers. Java provides us with a predefined class called property change support. So add property change listener will just go and say, hey, property change support, add this listener to your list. I don't want to bother about keeping the list myself. Okay, and I've got the get total score and the get final score. That's fairly straightforward. and I just instantiate this instance of this helper class to go and create my list. Okay, so there's no conceptual detail. And here's where things get interesting. Whenever set scores is called, I compute the new value of pass. Okay, and then I go and announce to the view all the things that have changed. So when set scores was called, the total score got changed, the final score got changed, and the pass property. Okay, when you say is pass, that's like creating that's defining a getter for a Boolean property. So that got changed. So all of these have names. Okay, and total score is the string total. Final score is the string final score, and pass is the string pass. And I go and announce to any observer that, look, all three, these are the new values. And you can display them. Okay? And one of the things that fire property change is something that property change support provides me. It will do nothing if the old value of a property and the new value of the property are the same. Okay? So if I do set scores twice with 60 and 80, and they're the same student, different students, it won't announce the new value. So I will go and there might be somebody that's actually showing the history of values. So it really needs the firing twice. So my reset properties after firing goes and resets the properties to null, so that my next time, and null is a value that you'll never enter. So this way I get the thing fired. Okay. So the main concept here is that the view model is informing the view whenever it's changed. To do so, it goes and uses a helper class. Okay. And that's how the helper class is being used. Okay, that's the main concept. Okay, questions? There's a lot of code here, maybe not enough time to process, but the concepts are few. Okay, so I'm doing this fire property change where I'm giving the name of the property, the old value of the property, and the new value of the property. And before I go and change my variables, I go and store the old values of these variables so that I have the correct value set. Okay, and reset properties just assigns them auto now. Okay, and property not fired if old value is equal to new value. That's the concepts. Okay, you can look at the code at leisure to understand it in more depth. And I haven't defined the isPass method quite. I just called the isPass method there, and now I have two concrete subclasses of the abstract class, and I already have a pass util I wrote in my previous version. Okay, so I'm not going to duplicate the code. That's just going to be utility stuff. And this one is pass here goes and calls a regular pass on get total score. Okay, another class which is takes a get total score and get final score and passes to pass util. Again, I don't repeat the code there. So now I have two different classes implementing the same interface. Okay, this is what I'm getting by doing all this work. Okay, the same interface implemented by two different classes, which can allow us to choose what we want. Okay, so there's really nothing new here. If I'm seeing some blankish looks, and that's because a lot of code has been presented here. That's just for reference. The concepts are few, that we've got single interface and multiple instances, multiple classes. Okay, questions? Do you have a question? Okay. Okay. So here's the concept here. So interfaces are great. It's a specification. I said you can change the class of something with another class in a program by having interfaces. Did you guys study a pattern, or do you remember a pattern that allows you to change the class you use for an interface? So delegation is an alternative to inheritance. Where did you study delegation? 401. So delegation is having a has-a relationship rather than is-a relationship. But I'm saying that, I have this interface, which is pass model. I described in the beginning. And I have two different implementations of it: a regular pass model and a flexible pass model. If I'm feeling generous, I go and give fudge points for high final. If I'm not feeling generous, I say, nah, Forget the final, just look at the total. So in a program, I want to go and change the interface, the class that implements an interface. Robert? Factory. Okay, Robert took my distributed systems class where we use factories a lot. Factories are also used in your assignment. Okay, that's why I'm kind of highlighting it. And I assume you guys in 401 study factories? In your KMPs 401? Maybe, maybe not. Yeah, I mean, to what depth one learns something, that depends on the class. Okay? Hopefully you learn something else in depth. Okay? But, so factory, somebody want to describe what a factory is? And not the factory analogy. What a factory class is?
You have like a class that is set that is an object, and you pass the parameters and specifications that you want for that object, and it decides which class you're going to implement for that interface that you're expecting that object.
So you don't go and say new directly. You call a method in a factory that decides which new to call. There may be more than one new that can satisfy your requirements. So you just say, I want a pass model. Hey factory, give me a pass model. And based on what the state of the factory, it says, I'll give you a regular pass model, or I'll give you this flexible, generous pass model. Okay? So, and it's particularly good for singleton classes, where you have only one object of that class. Okay? Because you say, give me that model. But in general, factories can be used for multiple also. So your factories, in your assignment, there's an expression factory. An expression factory will instantiate the expression objects. And we provide you with predefined expression objects, but you have to replace these expression objects with your own expression objects. Okay, and have the whole Lisp interpreter change. So that's what you'll be doing. So, so factory provides a static or instance method to return an object of some class bound after possibly instantiating the object to the factory. And it's particularly used for singletons, that you want to make sure there's only one instance of the class. So you make sure nobody does a new. The only thing that does a new is the factory, and it can do only one new. Or it can choose which new to do. And singleton is just a class with only one instance. Okay? And here's my factory. Whoever needs a pass model does not instantiate the pass model. It says get pass model. And the factory says, has somebody set a pass model for me? This is singleton. If somebody has set a pass model, I'll return that value. Otherwise, I'll make a choice. Okay, and I'll just say a regular pass model. Okay, and somebody else can go and set the pass model to be a flexible pass model or a high final pass model, and the factory will return that. Okay, so we will see examples of that. In fact, we're going to use this particular pattern a lot in the examples I'm going to show you next. Okay. Question?
Is a static class something?
Is this factory class itself?
Yeah.
So, is a static class singleton? No, not technically. Static class should have an instance. Okay, the whole idea, and why would you have a singleton rather than a static class? In Java, static classes don't have interfaces. Okay, you can't do substitution. Whereas singletons, you can do substitution. So it's being more object-oriented, but it's in the same spirit.
So every time when you return an object, you deep copy the content of object to outside, or just return the reference.
Every time you said you copy an object.
Every time you return an object, you do a deep copy to this object, or you just return the reference to this object.
Where did you study deep copy, by the way?
C.
Sorry?
C. C++.
Ah, good. So, you can have the notion of multiple pointers to the same object. You can have the notion of a shallow copy of an object, and you can have the notion of a deep copy of an object. Okay? I don't want to get into deep versus shallow copy. I do have a YouTube tutorial, YouTube video that you can look in depth. So I am not doing any kind of copy here. This is a singleton. There is only one model. and I'm returning that model each time. There's no copying going on here. Okay? So this is just a reference. I don't want to get into deep versus shallow copy right now because I won't do justice to it. I've got a 2-hour lecture on it. So you're welcome to sort of look at that. And if you want to, just send me a mail or post a message in the Piazza, I'll send you a reference. But I'm impressed that you know about deep and shallow copy. Other questions? And here's my view. Okay? My view happens to just implement the property change listener interface. I'll define a new interface that extends property change listener but doesn't do anything, just so that I can add methods to that interface later if I need to. Okay, I want to type everything with that interface, and Java allows me to go and easily do that. And the console view has, every time you do a file property change in the model with a property, this property change method is called with that event. And it doesn't care about the total score and the final score. It just cares about the pass property. And if the pass property has been passed, it goes and gets the new value of it gets the property of it gets the value of the property, and it prints out either true or false. Okay, with the is pass prefix. Okay, so it just does some. It doesn't matter what it does. Okay, but it does basically processes the pass property. So that's my view. Okay. Okay, so this is the reason why I have pass view, basically an empty interface, because I might change my mind. So this particular method is called in the view. Like I said earlier, that whenever we call a method in the model that changes the state, it invokes a method in the view, and is set with. And so I have a view factory also, and I have a controller factory also. So there's nothing interesting here. Okay. Oh, so this is, sorry, we have a view factory. Now here's the controller interface. It's the one that's doing input. Okay. So it has a process input method. There's no main, it goes and uses the pass util's input double thing. So it inputs the total score. If total score is less than 0, it breaks out of the loop. It gets the final score, and then it says, it needs the model. It needs to call the set scores method in the model. So it doesn't refer to the model. Since the model is singleton, it just goes to the factory and says, give me your model, and change it based on my score. So it's taken the input, converted that into some values, and called the set scores method. Okay. Okay, so it's using essentially, and a factory here, and MVC setup. MVC setup basically gets the pass model, it adds to the pass model, it gets the pass view, makes the view the listener to the model, and then tells the controller to run its loop to process it. Okay, so it's sort of all coming together here, that you're doing essentially what I said earlier. You're just connecting things together. Okay. So this is just in code what I showed you guys in diagrams before. So if this code is too much, ignore it. Okay. The point is the diagrams I showed you. And now I get to my main method. In my main method, I go and set the pass model, which factory to use. I tell the factory which model to use. And I've got two mains. One main that says use a regular pass model, and then goes and says, hey, pass util start MVC. Then I have another main that, sorry, this is a mistake. It should be high pass model. Oh, sorry. So that was a regular pass model, I think, and this is the pass model. So it basically it sets a different objects with the two factories, and now you see the reuse really helping. That you saw this whole infrastructure with model view controller, and I've shown you how I can just change the model without so easily if I have that infrastructure. Okay. So again, those diagrams I showed you are the main points here, principal points here. This code is just to help you concretely understand those diagrams. And we will go from here next to VECA or to statistical models next time. So again, those diagrams I showed you are the main points here, principal points here. This code is just to help you concretely understand those diagrams. And we will go from here next to VECA or to statistical models next time. Okay, so let's review what we did last time. We were looking at what Java offers in comparison to other languages, in particular languages like C that came before it. You notice that Java's syntax is quite similar to C's syntax. It made that, Gosling, the inventor of Java, made that decision. And you can have multi-file programs in C. Many of you haven't used that facility. And they're using file abstraction to break up a program. There's a language-supported abstraction called modules, which provides you with more functionality. And classes with just static methods essentially provide you with modular facilities. Okay, so if you just had classes with static methods, you'd call Java modular. We also saw that classes are also types. You can instantiate them. So you can we then saw through the factory analogy that you can unify both of these roles of a class by saying that a class has static methods and variables, okay, and an instance of a class has variables that are allocated dynamically. They are allocated from a heap, okay, and you can invoke instance methods on them. Okay, so this is stuff you know before, but this sort of makes it more clear how Java differs from a non-object-based language like C. So what exactly is object-based? We saw languages that are just don't put any walls. So those were the early languages, what I would call conventional based on my age, but not conventional to you guys. Then there were modular languages. So the examples of non-modular languages are Fortran, Algol 60, there are many such, Algol 68. So there were many such languages. And then in the 70s came Modular and Modular 2, maybe in the early 80s. And there were modular languages, but they were not object-based. Object-based means that you have both modules and instantiable classes. Okay, so the modules can be instantiated essentially, and then you get into object-based languages. Okay, so when you have instances of classes, you get any language that provides class instance is an object-based language. Okay, so you've studied rules of object-based languages in your 401, and so you probably think you know object-oriented programming well, and you probably knowing the theory well is not a difficult task. Okay, putting it into practice is extremely difficult, and that's where you need the help of others who have programmed before you on similar problems. Okay, and the programs that are unified by some common class structure. parts of programs that follow a common class structure are defined by a design pattern. Okay, and there are many design patterns, and this is not, we're not going to look at design patterns in depth here or at all here. That was 401, and there will be graduate classes also that will offer, that will tell you about design patterns. But I did go and introduce this model view controller design pattern to bring out certain features that we would like in object-based languages. Okay. And so the model view controller design pattern says that, look, any interactive program is going to have a user interface. Any user interface has got some input and some output. You may want to change the logic, the input and output all independently. Okay, lots of people think that the input and output are very tied to each other. And people are really lazy about decomposing programs anyway. So Smalltalk came up with the model view controller abstraction, and people said, let's just combine the view and controller into something, and we'll call it editor. That was a good term. But people also use the word view, which is a bad term. And that's the term used in the web MVC model. Okay. So we are not going to look at the web MVC model. And we'll try to bring out some aspects of language design that are motivated by the MVC model in Smalltalk. Okay. So we saw that observables. So in model view controller, you have a model that's notifying its views. So the model is an observable, and the views are observers. And the model might have views or observers of the implementing very different functionality. If they are implementing different functionality, then that functionality is in different classes. So you want to invoke in the model methods in these classes without knowing what these classes really are. Okay? So normally when you invoke a method, the compiler goes and puts the address of the location where the method should be called. That was done in conventional languages. And now you can't quite put the address there because you don't even know where it will be called. Okay? There are different implementations. So we need something called dynamic dispatch. And there were many ways to do dynamic dispatch. You can do it through subtyping. Okay. So suddenly I've got this new concept of subtyping. Okay, I said there were classes, there were instances, and now I'm saying there's inheritance. Okay, so the languages that are object-based and have inheritance are called object-oriented. Okay. Now there was a paper from Brown that went and defined these terms, and lots of people who read the paper followed these terms. Most people in this world today haven't read the paper, so they will go and use the word object-based and object-oriented interchangeably. But since we are in a language design class and we want things to be defined somewhat precisely, we will use these terms for different things. Okay. So we can have a superclass that defines all these methods, and the subclasses can override them, and at runtime, the overridden methods are chosen. Okay, so suddenly this becomes more like an interpretive language, that we are doing more things at runtime. Okay? The interpreter does everything at runtime, and here we are doing more things at runtime than what I call conventional languages do. Okay? And the ability to have a piece of code referred to work on values of different types is called polymorphism. Okay? So this is how you get polymorphism. This is a term you probably learned in 110-like courses and 401-like courses, and we get that with dynamic dispatch. Okay. And why did we go to abstract classes? You know, when you had the notion of superclasses, that's what Smalltalk had. Well, sometimes these superclasses are classes that are not instantiatable on their own right. I mean, it doesn't make sense. All they're doing is unifying a bunch of methods. Okay? So if you're doing that, why don't you go and tell the language, hey, this is not a class to be instantiated, so we call it abstract class. That was what C++ did. And sometimes these abstract classes have only method headers, only abstract methods. They have no bodies. So abstract classes with only abstract methods are a different entity. They're a specification. So we'll call them interfaces. But we don't have to call them interfaces. Interfaces were invented much earlier than C++. They were actually implemented in the context of modular languages, and people said, let's have all the static method headers in an interface so you can have two different modules implement the same interface. Or you can at least have the implementation and the specification part separate, so that somebody who's interested only in this specification doesn't have to look at the code. Okay? And what Java did was, and not just Java, there was a language called Eiffel that came before Java, said that, look, we'll have interfaces with instance methods also, okay? And then Java said we'll have interfaces with only instance methods, headers. So, so the notion of interfaces becomes interesting now, and interfaces is probably one of the last constructs that I'm going to talk about that was invented. It was done in late 70s. Okay, the first language I know that had interfaces was this language called Mesa from Xerox. Okay. And interfaces can support dynamic dispatch. You just say, when you're calling a method, you just say, I'm going to call a method from this interface. You don't know who's going to implement that method, and dynamically we'll choose the right method. Okay. Interfaces are good when you're going to have one object called methods in classes that implement multiple classes. Okay, the same method call is going to refer to multiple classes. Like a model goes and invokes a notify method and multiple observers, all of which can be of different classes. Interfaces are also good when you want to replace. So this is done at runtime. Sometimes you want to just change the implementation of a program of something with another thing. Okay, this changing is a big deal in software engineering, and we might want to do that at compile time or at runtime. So interfaces are good for changing also, substitution. Okay? And interfaces, like I said, the motivation in Mesa was that they're a form of documentation. So they play three roles, and so they're pretty important, even though people don't tend to use them as much as they should be. Okay. Questions so far? I'm reviewing here. I assume, but I know, I know not everything sunk in last time, so I can assume some lingering questions. So feel free to interrupt me anytime. Then the issue becomes, if you're really interested in changing the implementation of an interface, how exactly do you do that? Well, every place you did a new of class C1, you can replace that new C1 with new C2. Okay. Where new C1 may have been called, a million times, and you would go and figure out all the places where new C1 was called. So that is a problem. So what we'll do is we'll go and never do C1. We'll have a factory class on which you would invoke a method to instantiate, to create a value of some interface, and that factory class will provide a method to instantiate an appropriate class for that interface. And we can go and either invoke a method dynamically in a factory or change the factory statically to go and change the class that you want for the interface. Okay? And that's exactly a feature that you have to use in your assignment 1. We give you an implementation of an X expression object, and you have to replace that with your own implementation. Okay? And factories are independent of singletons but related. That often factories are used to ensure that you have a singleton. Okay, so a factory can always return the same instance each time somebody wants an instance. Okay, so that way people don't go and create multiple instances. Okay, so a singleton is basically a class with exactly one instance. Okay, and why do we, why do we create an instance at all? Why don't we just say, hey, the static methods serve the same role as what the instance methods of that instance would? Well, interface, like I said last time, objects implement interfaces that can be substituted. So in fact, you can have factories that produce factories. Okay, in fact, that's a feature I use extensively in the code we write. So we might want to replace one factory with another factory. So replacement requires interfaces, and in Java we can't put static methods, headers, and interfaces. Okay. So we looked at singletons and factories. And then I showed you a lot of code, and I didn't want you to look at the whole code. I highlighted parts with red, but you guys looked at the whole code, and that's when I was sort of losing you guys because you were looking at the details, which are not important. So I redid those slides, and I try to bring out the concepts more through code. So let's go and take this example that involves a model view controller implementation of our example application, and let's go and see how factories and model view and controller and interfaces all sort of play a role here. So we have a controller, model, and view, and we'll go and have the controller and view dependent on the interface of the model rather than the class of the model. That will allow us to substitute models. And in this example, can you imagine multiple models? Yes, you can imagine multiple ways of grading the final, grading the exam. The regular way is just look at the total score, and then these fudgy ways of looking at, hey, the high final and so forth. So we can have a regular pass model, which is not flexible, and then we can have a pass model, which looks at both the total score and the final score. So there are two alternatives. We may want to replace things at compile time, at run time. It's probably at compile time. You don't want to have different criteria for different users, for different students. Okay? So they both are extending an abstract pass model. So we were using an abstract class. And the abstract class model implements an interface, common interface, with some abstract methods in it, which are not important at this point. And I already have a pass util facility to do this all, so I'm not repeating that code. Okay, so two different interfaces for the model. I need a factory. So here's my pass model factory. It has static methods. Like I said, factories themselves can be objects with interfaces. But here I'm just being lazy and I've defined static methods. And it has got a variable that holds the current model. Okay, so this is a singleton class. There's always a current model, and you can go and somebody can dynamically go and say, this is your model. Okay, in which case it uses that model, or it has a method that goes and chooses one of the two models that it knows about, and it chooses a regular model by default. Okay, so here's the factory example of factory class. Okay. Questions? Okay. So it has got a get pass model and a set pass model, and it returns the same pass model each time once it's initialized. Okay, so now let's understand the controller model and view architecture and factory use. So the controller doesn't have a reference directly to the model. Okay, so what does the controller do? It processes input. So it's got a loop that repeatedly processes input. That's much like the loop we saw earlier without model view controller, except that after doing the input, it produces no output and it does no logic. For logic, it goes and finds from the factory the model, goes and says, hey, here are some new scores. And you do what you feel like with that. I'm done with that. Okay? And the model has to be responsible to go and convey that information to the view. The view is responsible for displaying it. That's none of the controller's business. Okay? So we are seeing here the use of both factories and model invocation methods. So what does the model do? The model does some logic to compute scores, uninteresting from our point of view. Okay? What's interesting from a point of view is that it interacts with the views, which are observers. Okay? And it uses a helper class to do so, which is again not interesting conceptually, but practically is interesting. And it goes and says, hey, my three properties got changed. Okay, a property is just basically a value with a getter and a setter. And I know I do that in depth in 401, and I know Ketan does that in his 401 too, so I won't belabor this notion of properties. And it says, look, three things changed. I got a new total score, the total score changed. I got a new final score, so the final score changed. And I computed a new value of the pass variable, so the pass variable also changed. Okay, or the pass property changed. It's both a property and a variable. And whenever it notifies its observers, it tells the observer, here was the old value, here's the new value. Okay? And if the old value and new value are the same, the helper class doesn't even bother to send a message. Okay, so here we are seeing the notification, the dashed lines in this picture. And that fire property change indirectly calls a particular method in the view, defined in an interface called property change listener, which is extended by pass view. And that method is called property change. That's defined by the interface, and it takes a property change event. And it gets three property changes: the final score, the total score, and the pass property. It ignores the pass property, the final score and total score properties, and it just goes and displays the new pass property. Okay? And it does so by just doing a print line. A more interesting view might go and show something graphically. It might show you the history of scores that have been done. But this one is just showing you the value. Okay, so we see that once the model, view, and controller are created, how they interact with each other. Okay, and this is sort of the small talk MVC design pattern. The issue then becomes, how do you connect them together? Well, we have another class to connect them. And that there's one class that says, hey, I'll go and get, somebody has to instantiate them, somebody has to connect them. So I've got some code to go and instantiate them and to connect them. How do you connect? We don't have to connect the view to the model because the view fetches the model from the factory. So we don't have to go and pass it to variable. Okay? We do have to tell each model all of its views. And the way you tell a model about its views is to call a registration method in the model. And that method is called add property change listener. And we assume we have a factory for the view and controller also. So this particular set of code fetches the model, fetches the view, fetches the controller, connects the view to the model, and so, you know, so that's how the connection happens. And now we have two mains, one that is the regular pass main, and one is that's the flexible main. And the mains just go and call the setup stuff after initializing the factory. Okay, so one main goes and says the factory to be used, tells the factory that the singleton to be passed is a regular pass model, and the other one sets the singleton to be a flexible pass, or just a pass model. Okay. So we see all of this come together. So where we had one method do everything, we have so many classes working together, and hopefully that will improve reusability. Okay, so model view controller, clear, and the concept, interfaces, dynamic dispatch. Any questions? Okay. Mac, are you fine? You're looking a bit, you're fine? Okay.